Inheritance. Hello everyone, this is Ben Finkel, and in this nugget, we're going to take a look at how we can implement the concept of inheritance in object-oriented programming in the Python programming language. Now, inheritance is a really important feature of OOP. It allows us to communicate structure about our data and our code, both up to the programmer ourselves as well as down to the actual program. So we'll start off talking about what object inheritance actually is, what kind of problems it's trying to solve, and how you can use it to define your data models. Then we'll jump right into the code. We'll take a look at basic inheritance. We'll inherit from my parent class down to a child class. In our case, we're going to use shapes and squares. Then we'll get into some more complex topics. We'll talk about method overloading, how you can define the same method over and over throughout your class hierarchy. And then lastly, we'll take a look at inheritance hierarchies. We'll talk about implementing multiple inheritance down a chain of classes so that you can have a good sound structure inside of your code. There's a lot to go over. Let's get going. One thing you're going to learn as you become a better and better programmer is that anytime you see code being repeated multiple times over and over inside of your program, you're probably not taking advantage of a feature that you otherwise could be. Take a look at this code sample here. So I'm defining a few different classes, a few different objects in this code sample. And I've got a square and a rectangle and a triangle, right? Well, notice that on each of these class definitions, I've got a self.color property defined. There's a member property called .color that I've set equal to a blank string because I want every shape that I create to have a color associated with it. And this would be true if I added on more shapes, circles or rhombuses or trapezoids, whatever. I want them all to have a color, and they've also all got a number of sides here. So every shape that I define inside of my program is going to have these two things. So why do I have to define that over and over and over on every single shape that I have? Why should I have to do that any more than once? Well, the short answer is I don't. I can inherit those properties from a different class that we call a base class using a feature of object-oriented programming called inheritance. And here's the basic idea of how it works. You start with a general abstract class definition for the type of objects that you're talking about. In this case, I've got a shape. And then you create new class definitions, and those new class definitions inherit the base class definition. So the base class might only define one or two properties. The new class, the inherited class, or derived class as it's called, is going to include both of those properties without any additional typing, as well as whatever additional properties it itself needs. And in this little tree sample here, you can see I'm imagining that polygon inherits from shape, and quadrilateral inherits from polygon, and rectangle inherits from quadrilateral, right? And you might have others. You might have a square down here that would also inherit from quadrilateral. You might have a trapezoid that would also inherit from quadrilateral. So each of these things inherits the properties of the base class above it, and those properties translate down to the derived classes. It's a little bit confusing, but take a look at how it would work in practice. Take a look at these two class definitions here. I've got a shape and a square. And the shape simply defines two properties local to the shape class, color and sides, while the square identifies a property called width. But notice down here, I never create a shape. I only create squares. And the reason I can do that is because here in the parens on my class definition statement, I've included a reference to the shape class. So square now inherits properties and methods from the shape class. And when I initialize my new squares down here, I have access to the properties and methods that are both in the square class, like I would expect, as well as in its parent class, its derivative class, which is the shape. So down here, I can reference my square width as well as my sides and my color. Now, one particular note here, I did have to call the init function on my shape class, and that's because of something called method overriding. We'll get into that a little bit later in this nugget. But just know that you got to make sure you call the initialize function for your parent class so that that initialize function runs. Over here, when I run this actual code, you can see that I get my properties out, 5 by 0 red and 9 by 0 red. And what's cool about this is even though I've set my shape defaults equal to red and 0, I can overwrite them, right? I can come over here and I can say, all right, every square may have a different color as well. So let's include that. And down here, I'm simply going to say self.color equals C. Then we'll make the 5 one, we'll make it blue. I like blue. And we'll make this one green. So there. Now when I run my code, you can see that I get blue and green out as the properties. So the color property defined on the shape class was inherited down into my square, and now it's available inside of any of my square objects. And in fact, it's available inside of any shapes that I create that might inherit from the shape class. I could go ahead and make a circle like this. Simply defining myself a circle class and telling it that it also inherits from shape. And then I do the same thing. I call the shape initialize function, only this time I'm setting a radius in a color. Circles don't have widths, they have radius. So now I can print out my circle radius and my circle color. And of course, then I can ignore the sides property. Circles, you don't really have sides. Maybe you could say they have 360 sides. But if we run this code, you can see that I get out my squares just like before, as well as my circle, which is a size 10 orange. None of those properties interfered with each other. So again, what I'm doing here is I'm creating the bottommost level object, the bottommost level shape, a square, a circle, etc. And I'm counting on inheritance to pass down properties and methods, we'll see in a minute, from the parent class into those children classes. Let's take a look at those methods now and see exactly how that works. One function or method that I could imagine every shape in my program might need is the ability to calculate the area of that shape, a calc area function. And I went ahead and defined one right here in my shape class. Notice that it's not defined in my square, it's not defined in my circle, but I'm still calling it down here on my square object, square1.calcArea. And that's because I'm counting on inheritance to pass that function down into my derived classes, square and circle, from the base class, shape. So we can see this in action right now. I'll just come over here and say, run my code. The very last thing that prints out is that 0, and that's because 0 is the result of my calc area function, even though I called it out of the square object. All right, that's great. But you know what? There's no real easy or simple way to do a universal area calculation for all the different types of shapes that I might have. Certainly not in the time I have in this nugget. So what I'd rather do is simply define an area calculation that's appropriate to each shape inside of my program. Something like this. Here I've gone ahead and I've defined a calc area function on my circle and on my square that are appropriate for those two shapes. So my square, it's width times width, and my circle, it's pi r squared. And that makes sense, right? And we can see that in action once again. I'm still just calling circle1.calcArea. So I'll go ahead and say run my code. And you can see it comes back with an area that is appropriate for the circle calculation. There's pi r squared based on my calc area function that was defined inside of my circle here. If I go ahead and change this to square 1, just to demonstrate how that works, we can see that it's going to calculate the area of my square 1 object, which is 25. 5 times 5 is 25. So the calc area function that's defined with the specific shape is the one that's being implemented or executing when I execute it against that shape. This is a feature of object-oriented programming called method overriding. And it's pretty straightforward, but it's worth talking about here. What we've done is we've overridden the method from the parent object with our new method inside of our child object. So we had access to that calc area parent method if we wanted it, but in cases where we needed to be more specific than that, we could override it with our child object. And this calls back to what we did on our initialization function, our constructor, on the base class. Recall that originally I created my shape class with a constructor, an init function right here. Then when I created the square function, I created a new init function, and although we didn't know it at the time, what I was actually doing was I was overriding the constructor function from the parent class. So now my square object has its own initialization function, its own constructor, and the constructor on the shape object never gets created, even though I'm calling a square object which derives from the shape object. Hence the reason that I need this little line here where I call the shape constructor, I call the parent class constructor, in order to execute that constructor function before the rest of my square constructor function executes. This is good sound practice. This makes sure that any constructor in my parent class gets executed along with the constructor function in my derived class. You want to make sure you do that. And of course, because of the rules of inheritance and overriding, if I had not defined an init function down here in my square, then the shape constructor would have been executed automatically. So I don't have to have an override function in my derived class. It looks up the chain. The rules are to walk up the chain from the most specific and look for the first example it runs into in the least specific object. Same thing with calc area. If I don't define it on the square class, then this calc area function gets run because that's the first one that it's going to run into when it walks up the inheritance chain. Now you might be thinking to yourself, well, this hasn't done a whole lot for me, right? The definition of my calc area function in each of my shapes is really the exact same way I do it regardless of whether or not I inherited or derived from a base shape class. I could get rid of that entire shape class, that entire shape definition, and these calc area functions would work exactly as is. So what have I gained? What have I done by creating a base class and inheriting that value from that base class? And the answer is a couple of things. One thing that you've gained is a lot of readability and a lot of future proofing for future maintenance. After all, you can imagine that programs take a long time to write. You don't write them in an afternoon and then be done with them. They take weeks, months, even years you'll spend working on individual programs. You'll frequently come back to programs that you haven't worked on in a long time. You'll come back and work on programs that someone else worked on, or they'll come back and work on programs that you worked on. By including a calc area definition in the shape class, you are effectively communicating the structure of your shape objects to yourself and any future programmers that might come along and work with your code. So if I come along and I introduce a new shape, like a triangle shape, but I forget to add a calc area function definition in my triangle shape definition class, as long as I inherit from the shape class, that triangle will have a calc area function associated with it. It won't calculate the area correctly, but it will have this calc area function inherited from the shape class down into my new triangle class. And that's important. That means that the introduction of my triangle class will not break my code. It will not cause an error. It just means that my triangles won't calculate the area properly until I write that area calculation specifically. And there's another cool thing that you can do with base and inherited classes. Check this out. Here I've made a few different changes to the code. First of all, I created that triangle class like we talked about, and it simply takes as its constructor 3 values for the size of the 3 sides of the triangle and a color, so kind of similar to the ones above. But notice I don't define a calc area function on the triangle. I also took out the definition of the calc area function on the shape just temporarily, just to demonstrate what's going to happen here. So even though my triangle inherits from shape, there's no calc area function definition inside of my triangle class. Then down here I created a function that's simply called print area, and all this function does is take an object and call the calc area function on it. So the parameter that we pass into this print area function must have a calc area function, otherwise we're going to get an error inside of our code. So if I come down here and I call print area against square 1, which is what this code looks like right here, that ought to work because we have a definition for calc area inside of our square 1 class definition. And I go ahead and run it, and we can see that it runs just fine. It comes back with 25, which is what we'd expect. But if I create a new triangle object, let's call it T1, just like that, and I pass T1 into my print area function, now when I try to run this code, I'm going to get an error like we talked about. So here it is. It says, oops, I gave it too many parameters when I passed in my new triangle function. I left off the underscores on my init definition, so missed my my constructor definition syntax there. Save that and run it again. So here you can see it says that triangle instance has no attribute calc area. That is the error message that I got back when I tried to print the area of a triangle. So again, I've forgotten to define calc area on my triangle. Now my code crashes out with an error, an ugly error that doesn't mean anything to the user. I don't want that. So what I want to do is I want to make sure that my shape class, my base class, has calc area defined. So now I know that no matter what else happens, even though I don't have calc area defined on my triangle, my code won't error out. It's simply going to return a 0. It's going to return that base default version of the class. So my print area function is pretty cool. It's taking a type, or is expecting a type of the base class of a shape right here as S. It doesn't care what kind of shape it is, triangle, square, whatever. It just needs to know that it's a shape class and that it's going to have a calc area function available to it. And as long as it does, it's going to execute without an error, at least without a syntax error. Maybe the area doesn't calculate accurately, but it's not going to have an error that's going to crash my program. So we've passed in a parameter by our base type, but we can pass it in actual usage down here by any of the derived classes that derive from that base type. Pretty powerful. The rules of inheritance also allow us to handle multiple inheritance, similar to that tree view that I showed off in the first slide at the beginning of this nugget. So here I've created a new class called quadrilateral, right? The quadrilateral is a more specific type of shape, but it's not super specific. And the point of this is to say, you know what? I've got my shapes. I've got a quadrilateral that inherits from shapes. And notice that I define the number of sides on a quadrilateral as 4. It's sort of the defining feature of a quadrilateral. And then down here on my square class, I'm actually going to change my inheritance from shape to quadrilateral. And the point here, of course, is that now I've got multiple layers of inheritance. Shape inherits down to the quadrilateral. Quadrilateral inherits down to the square. And all of the features, all the functions are passed on down through this chain of inheritance. Notice quadrilateral does not have a calc area function, although it certainly could, but I have it defined on my square. And if I call a new quadrilateral, it's going to inherit from shape, and it's going to have all the features of a shape. But when I create a new square, it's going to inherit from quadrilateral and have all the features of both the quadrilateral and the shape above it. This is direct inheritance, multiple inheritance. We can do this over and over and over. We can create a whole structure of objects, in our case polygons, that reflect the actual properties of polygons inside of our code structure. And in fact, if I wanted to really accurately model that, I would change my code to look something like this. So here what I've done is I've moved all of my initialization, my constructor information, up into my quadrilateral constructor. So that's where I'm going to define my number of sides equal to 4. It's going to take a width and a length and a color. So quadrilaterals have both a width and a length. And I've also defined my calc area function in my quadrilaterals. What's great about quadrilaterals is the area calculation is the same for all of them. It's width times length. Then down here, I can reuse my initialization function. I can override it to only accept a width and a color. Because a square has the same width and length, I only need to accept one property when I create a new square. So I have the ability to both create a new quadrilateral or to create a new square. But now I've got a change that I need to make down in the initialization function in my constructor on my square. It was referencing shape, but you know what? Now I want to reference quadrilateral because now I want to call the immediate parent or the immediate super class constructor function. So I got to change that to be quadrilateral. I'm going to pass it myself. I got to pass it a width and a length. Well, that's going to be the same. It's going to be W for both of them because this is a square, and then the color that was passed in. So here what I've done is I've overridden the constructor function from the quadrilateral down here inside of my square, but then I'm calling that function with the values that were passed into my square constructor function. Pretty neat, right? I've got my definitions coming from abstract down to more specific, down to super specific. And if I come over here and execute this code, we can see that it executes just fine. I passed it in a square shape into my print function, and I got 25 out. Notice that my sides are also 5 by 4 and 9 by 4 because I defined the number of sides up here in my quadrilateral. Even though I created square objects, which don't reference sides anywhere inside of the square object, it inherited from the quadrilateral. Now, one problem that we had here is that we had to change that initialization function, that super call, down here inside of my square. When I changed where square inherited from, I also had to go down here and change it in this code. And that's kind of a problem, right? That's not a good flow. We only want to change things or define things in one place. Well, what I've done here is called classic class definition in Python. It certainly works. You can certainly do everything here. But you can make life a little bit easier for you with a little bit more complex code. And all you have to do is, at your very base class, inherit from something called object, little o object. Go ahead and save that there. With this little change, I'm now using something called the new style class definition. And this allows me to change the way I call classes in my superclass, in the parent class. So down here, instead of a reference to quadrilateral, I can make this code look like this. Here I've gone ahead and made a change to the way that function is defined. Now I'm just calling this generic function super, passing in a square object, and myself calling the init function and passing in the remainder of the parameters. What I've done is I've abstracted out that call, so I no longer have to definitively refer to shape or quadrilateral in my super call. Instead, what I've done is I've said, hey, call the initialization function on whatever the direct parent of this quadrilateral class is, and that will change automatically depending on what I'm inheriting from down here. So because square inherits from quadrilateral, it's going to call the quadrilateral definition, the quadrilateral constructor function. Down here on my circle, I'm inheriting directly from shape, so I can simply say super circle, comma, self, and I no longer need to put self back here now. And this is going to do the exact same thing, but once again, my super function is now dynamic based on what my circle is inheriting from. So this same little bit of code will ensure that regardless of what I'm inheriting from, or if I change it down the line, if I introduce a new ovoid type of class in between shape and circle and then inherit circle from ovoid, my super function will call the ovoid constructor instead of the shape constructor, which again is ideal. We want to maintain that chain, that hierarchy of inheritance inside of our code. That concludes this nugget on inheritance in the Python programming language. Just to recap, we talked about what inheritance is. We talked about how we can create a tree structure, a definition of our objects that go from abstract to specific. So we can start with shapes, then go down to quadrilaterals, then down to things like rectangles and squares. And at each definition, we can define more and more specific functions and features of those objects, of the data model. That helps us as the programmer understand how the code works and how it's meant to be used, and it also helps the code understand how the data is meant to be used, and it helps prevent runtime errors that are going to break your code and cause it to drop out. We looked at basic inheritance, how we simply inherited a square from a shape by including a shape inside of the class definition of the square. Then we talked about method overloading and how we overload the constructor functions, how we can overload any of the base class functions inside of our more specific inherited classes. Lastly, we talked about inheritance hierarchies. We showed how we can inherit down a chain of multiple different classes in order to have many graduations or many levels of specificity inside of our data model. I hope this has been informative for you, and I'd like to thank you for viewing.